In today's lecture, the concept of auditory filtering and psychoacoustics. And so this will be the last of our discussions on how the human brain is processing audio and what the relevant repercussions of that are when we want to process and prepare audio and make it available to the human auditory system. So this is taken from the textbook, chapters 5 and 6, and then also portions of it are taken from a Wikipedia article that's nearly identical to what is in your textbook, but had, I thought, slightly better graphics and the organization was a little more clear to me. So, auditory filters and psychoacoustics as audio is processed in the human brain. So, as an introduction to audio filters and a bit of our motivation for why to look at this, as far as the way humans do it, is that when we talk about frequency analysis and decomposition of an audio signal, we're almost always talking about it for the purpose of processing speech, music, or other important auditory inputs, usually for the purpose of either human interaction, human entertainment, or a machine learning natural language processor kind of thing. Whatever the application, it's important to understand how the human auditory system works. And if you really want to be effective with your applications, such as audio compression, speech recognition, speech coding, etc., what you really want to do is, as best as possible, you'd like to mimic aspects of the human auditory system and gain a fundamental appreciation of the way humans and mammals perceive audio frequencies before you really go much into processing that for applications. For speech analysis applications, such as speech recognition, it's often most effective to isolate and characterize the spectral envelope of a small temporal section of audio. And this is because it's been found in the vast majority of cases that the semantic meaning of speech is not really dependent or contained within the pitch or excitation component of the speech signal. So methods to characterize this short-term spectral envelope include the short-term Fourier transform, which is usually implemented, as we've seen, using a windowed FFT, or linear predictive coding, which we'll discuss a little later in the class this semester. Historically, such a characterization and analysis have been achieved using a bank of overlapping bandpass filters, often referred to as a filter bank. And this is in many ways, as we've discussed when talking about the cochlea and the basilar membrane, this is how the human ear works. This structure of a set of bandpass filters are known as critical bands, and this is the current consensus view of the human frequency analysis or human mechanism, and will be explored in a little further detail in this lecture. So this is just a graphic that illustrates left ear and right ear and left cochlea, right cochlea, and what happens once you get the cochlear response communicating through the auditory nerves. So you have the left cochlea and right cochlea nucleus, left and right superior olive, the left and right inferior colliculus, left and right medial body, and eventually the auditory cortex, where the signal has been pre-processed, pre-filtered, temporal and frequency adjustments have been made to the signal for the purposes of interpretation, which then begins in the auditory cortex so that we can perceive, understand and respond to the auditory inputs. So this, during the entire process, you have a left ear, right ear thing, and because we have two ears and there's some separation distance between those two ears, that helps for processing three-dimensional aspects of speech, as we've discussed before. But communication between the left and right parts of the auditory system happens back and forth throughout the entire scheme of the auditory processing system, all the way to the auditory cortex. So the left cochlear nucleus is also talking to the right superior olive, including as well as the left superior olive. So there's communication between left and right side throughout the auditory system. Critical bands. So auditory critical bands, and this is speech processing and audiologist language, are defined as a range of audio frequencies. And within that auditory frequency range, you have a masking tone that will interfere with the perception of another tone due to various mechanisms of auditory masking. The understanding and use of critical bands is key for implementation of perceptual frequency-based audio processing used in applications like wideband compression, including MP3 type files. So in order to understand the frequency audio domain, we have to understand this idea of frequency to place transformation. So in this model, the theory is that each audio frequency relates to a specific place within the human cochlea, and specifically a position along the basilar membrane. And then, as you've seen, an audio wave enters the ear. It has its vibrational characteristics transmitted to the oval window due to a vibration of the tympanic membrane and the ossicles. The vibration of the oval window induces a vibration of the coiled basilar membrane. For a pure tone, the maximum magnitude vibration of the basilar membrane is located at a specific physical position along the basilar membrane. And this position, the position contiguously ordered in terms of the fundamental frequency of the tone. As the distance from the oval window increases, the width of the basilar membrane increases and its stiffness decreases. So here's an illustration of distance from the oval window, and as a function of that, what is the response to a tone at 200 hertz. So we have a 200 hertz tone in the figure shown in the middle. And basically, you can see the response peaks here at just under 30 millimeters from the oval window. And then depending on the frequency of other tones, which are also illustrated here, we can see that where this peak physically moves. Now note that this is not an impulse response type of thing. So you do get some stimulation in other regions spatially. It's just that the peak occurs at a very specific location for a given frequency. So these critical bandwidths were experimentally measured, and a lot of observation and data was taken, particularly in the late 80s, early 90s, to sort of, and this was about the time that cochlear implants were being devised and improved. So it was about this time when some of the very early work on cochlear implants was being done in order to address deafness issues. And in order to do that, people had to understand this idea of frequency and place within the human cochlea. So this attempt was made to measure the width of the critical bands of these built-in auditory filters within the human inner ear, using test tones and co-located wideband noise. And so we'll see a couple of figures on the next page that illustrate this a bit. So the important thing to measure or to think about is this threshold of perception. So your threshold of perception is just the instant when you begin to hear a tone. And it varies for everyone, but there's kind of a cutoff for normal human hearing that you should be able, within this certain number of dB that is the threshold, you should be able to perceive the presence of a single tone. So you then look at how that threshold of perception changes in the presence of wideband noise. So the noise has a set bandwidth and it's centered over the test tone. The bandwidth is varied, and what that does is that changes the threshold of perception. Now, what happens is, as the bandwidth of the noise increases, so does the intensity of the threshold of perception of the co-located tone up to a certain point. Past that point, this threshold does not increase and stay steady at the same value. And so this was done for frequencies across the human hearing threshold. So what are they saying? They're saying that you can hear this tone. And so suddenly we introduce some band-limited noise whose center frequency is centered at the frequency of the tone. When that noise is loud enough, it completely covers up the presence of the tone. You can no longer hear the tone. So the intensity level of the tone has to be increased. Okay? If you increase the bandwidth of the frequency band of the noise, if you increase its bandwidth, then you are more likely to cover up or mask the test tone, which means that you have to raise the intensity of the test tone even more. So that's what they're saying that the threshold intensity has to be raised as the frequency bandwidth increases. And so here's a kind of a picture that illustrates that. You basically have your noise, and it's increased in bandwidth. And what happens is you have this critical band that's a function of the geometry of the ear, and we'll kind of represent it here by this Gaussian shape. What happens is once your noise window exceeds the width of the critical band, then it's no longer influencing what is inside the band. So as you have this bandwidth of your, what we'll call your masking noise, so this is your noise signal and it's got some bandwidth, as you increase the bandwidth of the noise, you must increase the signal intensity in order to be able to hear it. So this is what's being referred to as the signal threshold. That situation continues until the critical bandwidth reaches a point where you no longer have masking occurring at the frequencies that are on the lower and upper end of the bandwidth of the noise. The reason is those frequencies have exceeded the limits of this critical bandwidth of this particular region of the cochlea. So frequencies lower than or greater than this critical bandwidth are not going to impact the perception of the sound. Why? Because that critical bandwidth, that region of the cochlea that's responding to signals within that critical bandwidth is connected to and stimulating a specific set of auditory neurons. And if you exceed that region, that frequency bandwidth, so that you're now in critical bandwidths of other sections of the cochlea, those are different auditory nerves. So it's like there are a set of auditory nerves that are unique to that particular critical bandwidth. And so this is referred to as kind of this local auditory filter. And so in order to retain the signal to noise ratio, as you increase your noise bandwidth, you've got to increase your signal threshold. But eventually, when you reach the stop bands of the internal human auditory filter, the perceived noise for that particular neuron remains constant. So people came up with words and terms to sort of represent these critical bands. And the first one, and still one of the most common ones, was the Bark scale. It's basically usually defined as a table of frequency values, and they represent the center frequencies and the frequency ranges of these critical bands, taken from an original publication and going to be shown in the table on the next page. In addition to the table, there are analytical expressions that were derived for conversion between frequency and the Bark scale. The usefulness of this for people in engineering and audio engineering who are doing signal processing, this conversion is, debatable. So we'll look at the table. So here are the Bark ranges. So you have Bark 1, Bark 2, etc. Bark 1, the center frequency is at 50 hertz, and the frequency range is from 20 to 100. And then scale 2 is centered at 150, with the frequency range being 100 to 200, and so on. And they are, as you know, mostly symmetric about the center frequency, and they increase in width as your center frequency gets higher. So here is one analytical formula that will generate a relationship between frequency in hertz and the Bark scale. And there's a couple of them. Here's another function that gives a good approximation. Some MATLAB code that would relate the two. And you can see this plot where we show Bark. So this would be your 1, 2, 3, and so on. And then this is frequency in hertz. And the individual little pluses are the Bark numbers, and the solid line is the plot of the equation. You can get a simplified version of this equation from equation 5.3. This makes a few assumptions, but nothing that is really a problem for implementation. It's sometimes used in feature extraction for speech recognition, so sometimes that will be expressed in terms of the Bark number as opposed to a frequency range, just because that's audio talk. So yeah, this is sometimes an important part of a feature space if you're doing recognition. The other scale is the MEL scale, short for melody, also derived very early. Also relates a unit called MELS. The MEL scale can be converted also to frequency in hertz, and it is more often used in music. So once again, a plot that relates MELS to frequency, and and the MATLAB code that would generate said plot. So I'm not going to go into great detail about how these measurements were done experimentally, but I do want to talk about the concept of auditory masking, because basically what's going on when you superimpose this white noise over a tone is you're doing auditory masking. So I want to go a little more in depth into what auditory masking is, primarily because there's been a resurgence of the popularity of looking at auditory masking for the treatment of tinnitus. So people don't know what to do about tinnitus. There's no cure, there's no treatment, and there's no real understanding of what causes it, other than it's somehow related to hearing damage, but it occurs in the brain, not in the ear. So auditory masking is one technique, albeit a rather crude technique, being used. And some people, may do this on your own. I don't know. Occasionally, if I take too much Advil, it'll cause a little ringing in my ears. When I had COVID, I had tinnitus. I found that sleeping with a fan would detract from that, and I wouldn't really notice it. Also, the presence of other noises. If I'm talking, if I'm, as I am now, sitting and listening to traffic noise outside, I just do not notice it. So auditory masking is probably something you do quite often if you have noisy neighbors in your apartment. Maybe you crank up your own music, which provides similar auditory masking to the point where eventually you will no longer hear them. You don't want to auditory mask at a single tone or at a similar frequency only. The reason you want to audio mask with noise is if you try an audio mask with something that is a single frequency or harmonics, you'll be more likely to get a beat frequency effect with the sound you're trying to mask. So using white noise for masking is more effective. So in auditory signal processing, auditory masking occurs when the perception of one sound is affected by the presence of another sound. In the frequency domain, this is known as simultaneous masking, frequency masking, or spectral masking. In the time domain, it's known as temporal masking or non-simultaneous masking. So let's talk about the masked threshold. So an unmasked threshold is the quietest level of the signal that can be perceived without a masking signal present, while the masked threshold is the quietest level of the signal perceived when combined with a specific masking noise. So the amount of masking is the difference between the masked and the unmasked thresholds. So you remember early in the lecture we were saying that these critical bands were sort of defined by continuously increasing the bandwidth of the white noise played simultaneously with the tone. And as you did that, it raised the threshold level. So this is the threshold they were talking about. The amount of masking is the difference between the masked and the unmasked thresholds. So for example, let's say you're sitting at home and you hear your cat scratching at a scratching post. And if it's an otherwise quiet environment, so there's no other noise, for average people, the first audible sound is 10 dB sound pressure level. So remember, sound pressure level or acoustic pressure level is just a logarithmic measure of the effective pressure of a sound relative to a reference value, so 10 dB SPL. However, in the presence of a masking noise, so let's say someone turns on a vacuum cleaner, it runs simultaneously, you cannot detect the sound of the cat scratching because your vacuum cleaner is going to be about 26 dB. So we would say that your unmasked threshold for the cat scratch sound is 10 dB SPL, but the masked threshold is 26 dB SPL. And so the amount of masking is the difference between these two thresholds, or 16 dB. Simultaneous masking occurs when a sound is made inaudible by a noise or an unwanted sound of the same duration as the original sound. So a powerful spike at 1 kilohertz will tend to mask out a lower level tone at 1.1 kilohertz. Two sine tones at 440 and 450 can be perceived clearly when they're separated, but they cannot be perceived clearly when presented simultaneously. If two sounds of different frequencies are played at the same time, the separate sounds can often be heard rather than a combination tone. So I did a lot of work on this at one time when I worked with an audiologist colleague many years ago, and he was very interested in this, that if the sounds are close enough in frequency and they're played together, you cannot perceive the two different sounds. But if there's even the slightest time delay between the beginning of the two different sounds, that you suddenly switch to a different mode and you can perceive the difference. So even if they overlap in time, but they're not completely simultaneously, you can hear it as two tones. Whereas if they are totally simultaneous, you do not hear it as two tones. So this ability to hear frequencies separately is known as frequency resolution or frequency selectivity. If you are hearing them as a combination tone when they're played simultaneously, then they reside in the same critical bandwidth and they're exciting the same part of the auditory nerve. So this occurs obviously due to filtering in the cochlea, the hearing organ in the inner ear. Complex sound is split into different frequency components. These components cause a peak in the pattern of vibration at this specific hair cell inside the basilar membrane within the cochlea. So these components are then coded independently on the auditory nerve. It transmits sound information to the brain. Individual coding occurs only if the frequency components are different enough in frequency. Otherwise, if they're in the same critical band and they're coded at the same place, they're perceived as one sound instead of two. The filters that distinguish one sound from another are called auditory filters, listening channels, or critical bandwidths, as we discussed earlier. Frequency resolution occurs on this basilar membrane due to the listener choosing a filter which is centered over the frequency that they expect to hear, the signal frequency. So if you have a sharply tuned filter that has good frequency resolution, and it allows the center frequency through, but not other frequencies. So just an interesting thing about how, this perception of different or separate or combined tones when presented simultaneously or slightly delayed. So we also know that if you have damage to the cochlea and the outer hair cells in the cochlea, that impairs the ability to tell sounds apart, which explains why someone who has hearing loss due to the cochlear damage would have more difficulty than a normal hearing person distinguishing primarily between different consonants in speech. And if you don't understand the consonants, then you really can't understand speech. Now, masking illustrates the limits of frequency selectivity. So if a signal is masked by a masker with a different frequency to the signal, then the auditory system was unable to distinguish between the two frequencies. So by experimenting with the conditions where one sound can mask a previously heard signal, the frequency of the signal and the frequency of the masker. The frequency of the signal depends on the frequency of the signal and the frequency of the masker. So that determines the threshold of when you hear the signal. So these graphs shown on this page basically illustrate this concept for different frequencies. So you see this upper right one has a frequency of 250 hertz, and that is that's your masker, which has the same frequency as the signal. The amount the masker increases the threshold of the signals plotted, repeated for different signal frequencies. So you can see here's the masker, and it increases the threshold significantly at 250 hertz. But if the signal was, say, 1 kilohertz, say up here, then notice the increased threshold is lower. The different curves represent different intensities of the masking signal. So you can see that at low intensities, the masking signal doesn't have much of an impact. It has its highest impact, though, at 250 hertz because it's centered there. As you increase the intensity of the masking signal, you then have to raise the signal at 250 kilohertz more and more. But notice if you're up here at 1 kilohertz, it's not until you reach this third curve where you begin to have a little bit of impact, but very little, not really until the fourth curve where you really begin to have an impact on the threshold of hearing right here at 1 kilohertz. So if you were to go back and look at the Bark scale, you would find that that 1 kilohertz is in a different critical frequency band. Notice that this is illustrated not just for the masking signal centered at 250, but also 500, 1000, and 2000 respectively. And it's a little hard to tell because this axis is on a logarithmic scale. So you can notice that this bandwidth of influence is narrower at the higher frequencies, but you can't really say it's half the size because this is a logarithmic scale on the horizontal, but it is definitely less. It would probably, it's just hard to say with the logarithmic scale. Also notice that it looks a bit more symmetric as you go to the higher frequencies of the masking central frequency of the noise. So this is a bit more symmetric about this frequency than, say, the ones at lower frequencies. Also notice that it is easier to mask a signal with a frequency that is higher than the center bandwidth of the masking frequency than it is to mask one that is lower. So in other words, if you're masking at a kilohertz, that's not going to do a great job of changing the signal threshold or masking sounds at lower frequencies. On the other hand, because of this kind of extended tail, a masking center centered at 250 hertz is doing a fairly decent job of providing some masking at the higher frequencies. So the effect is a little bit asymmetric, more dramatically so at lower frequencies. So figure B basically shows the y-axis as the amount of masking. The greatest masking is when the masker and the signal are the same frequency, and this decreases as the signal frequency moves farther away from the masker This is called on-frequency masking, and obviously occurs because the masker and the signal are within the same auditory filter, so the listener can't distinguish between them, and they're perceived as one sound, with the quieter sound being masked by the louder one. The amount the masker raises the threshold of the signal is much less in off-frequency masking, but it does still have some effect because, as you could see, it overlaps into the auditory filter of the signal. So off-frequency masking requires the level of the masker to be greater in order of magnitude to have a masking effect, and that's shown in the figure here at the end. So, for example, here is your listening channel of the auditory filter. Here is your signal. You are masking off center, and you're actually almost entirely out of the critical band, but you do have a little bit of overlap. And remember, as long as you're within this band, the masking ability is a function only of the intensity of the masking signal, because it's the same auditory nerve being excited, same neurons being excited for all of the frequencies within this band. So just a little bit of overlap. Now go back and remember that our masking effect is asymmetric and has more of an effect on the higher frequencies. So all of this is telling us if your masker is centered at a frequency that is lower than the signal, even if it is at another auditory band, the impact overlaps in the band containing the signal, and you will still get some masking effect, but this masker will have to be louder. So if you want to cover up all those high frequency noises, you have to have a louder mask. As I understand it, tinnitus occurs clinically two different types. One is a very high-pitched ring. That's the kind that I experience, and mine is transient. The other is more of a lower, almost roar kind of sound. And I think that might be more common in men. It's more like a roaring in the ears. Whereas the one that I've experienced when I had COVID or as a result of certain medications was very high-pitched. So very different approaches to how to handle those two kinds of issues. So at the lower frequencies, and I believe these statements just summarize what I just said. As the masker frequency increases, the patterns become compressed, meaning that high frequency maskers are only effective over a narrow range of frequencies. And once again, that is relative, because remember, your scale was logarithmic. So talking about narrow range is relative, because if you look at the bandwidth of those two, the higher frequencies obviously higher bandwidth, but because you're at higher frequency, you're looking at, cues or things like that sort of have a normalizing effect. That would be a reasonable statement to make. Lower frequency maskers, on the other hand, are effective over a wider frequency range. So if you have to choose, better to choose a lower frequency masker. Okay, I think that this is primarily a restatement of some of the previous things that we have said, other than to just say that this is just a different way of illustrating kind of what we've already said, that the bandwidth of the masker within the auditory filter masks the tone, but the masker outside the filter has no effect. It is interesting to note that in MP3 files, this concept is used to reduce the size. MP3 utilize audio compression, so it's not, that's one of the ways that they transmit more easily, as they reduce the bandwidth. So parts of the signals that are outside of the critical bandwidth are represented in an MP3 file with reduced precision, and the parts of the signals that are inside the critical bandwidth have a higher precision. So it's analogous to in image processing. One of the ways image compression is done, let's suppose you have an image of blue sky and you're looking at aircraft, or blue ocean and you're looking at ships, and you're trying to encode the features of the aircraft or the ship. with a fairly continuous background. So in that case, you might take all of those pixels represented in the background and compress them down to one, for a given frame, compress the blue ones down into one single bit of information. And then the decompression would have an algorithm that would, correspond to pixel ranges that were pre-encoded. So you can do the same thing with audio. When you have information that is outside of the critical band, you can represent it with reduced precision. So varying intensity levels obviously also have an effect on masking. The lower end of the filter becomes flatter with increasing dB, so that if you look at this, you see these are sloped. These do not have as much of a slope as you get to the higher intensity, the higher dB. And the higher end of the slope becomes slightly steeper. So these are less consistent at the high frequency side than they are at the low frequency. At medium frequencies, the slope increases as the intensity increases, but at the low frequency, no inclination with level, and the filters or high center frequencies show a small decrease in slope with increasing level. So in other words, the sharpness of the filter depends on the input level, not the output level to the filter. The lower side of the auditory filter also spreads with increasing level, and so some of these are illustrated in figure H, shown below. So the other kind of masking that you can have is you can have temporal masking or non-simultaneous masking. And that occurs when a sudden stimulus sound makes inaudible other sounds that are present either immediately preceding or following the stimulus. So masking, which obscures a sound immediately preceding the masker, is called backward masking or pre-masking, and masking, which obscures a sound immediately following a masker, is called forward masking or post-masking. So temporal masking's effectiveness attenuates exponentially from the onset and offset of the masker. The onset attenuation lasts about 20 milliseconds, and the offset lasts about 100 milliseconds. Similar to simultaneous masking, temporal masking reveals the frequency analysis performed by the auditory system. So forward masking thresholds for complex harmonic tones, a sawtooth probe with a fundamental frequency of 500 hertz. They exhibit threshold peaks for frequency bands centered on the first several harmonics. In fact, auditory bandwidths measured from forward masking thresholds are narrower and more accurate than those that use simultaneous masking. Temporal masking should not be confused with the ear's acoustic reflex. So the acoustic reflex, we talked about this. It's this involuntary response in the middle ear that's activated that protects the ear's delicate structures from loud noises. So this is different. Best thing I can think of to give a real-world example is when you're watching a news broadcast and they're, broadcasting a report showing someone possibly letting loose with a string of expletives, and you get the beep. So that's an example of temporal masking. The beep kicks in almost immediately following this string of expletives. And most of the stuff done in the news and things like that, they've taken the video and it's post-processing. But you can do this in real time under certain circumstances, especially if you integrate some machine learning to sort of do some prediction of what's coming. You can have the masking kick in immediately following, and from the human perception, it obscures what's being said. Now we'll talk, let me see where we're going next. Before I talk about this, I will say that, so masking occurs all the time, and with hearing loss, it becomes even more dramatic because like normal street sounds will now begin to mask. I have a family member who is very, very sensitive to traffic or fan noise, and when you're talking to them, they have virtually no hearing when there's this background noise. So they're very sensitive to this threshold effect. And for them, it's quite low. They don't need much noise to not be able to hear. or not be able to hear accurately. Now, the interesting thing is, though, if you do some experiments and you look at comprehension of humans to speech, if people, and this includes people who are not lip readers, if people who cannot lip read are even just like watching someone speak, you can lose up to about 70% of the auditory content of the speech, but your integrative sensory perceptual regions in the brain will take simultaneously your auditory input along with your visual input, and will do a sensory integration task that interprets the speech in real time based on cues that you get from what you see, as well as the, not just the lips, but the overall scene and the overall context. So humans actually can lose a great deal of hearing, and if their visual system is engaged, then they really don't even notice that it's gone. People will go and have auditory testing done and have virtually no idea that they've lost hearing. Usually it's a family member or someone external who notices that their hearing is gone, but the person who actually is hearing impaired often has no realization, because their awareness when they're also looking and seeing, and this compensatory network in the brain that allows for you to integrate your visual with your auditory perception is so effective. That is why it's difficult for people to watch movies that have subtitles, because you don't get the cues from the the visual cues, because the person is not speaking what's in the subtitle. So it can be very confusing to try to do that. Okay, so I'm going to stop the video at this point because I don't like making videos that are too long, and we will come back to this particular slide to complete this series of lectures.